welcome back to 10.418, 618. Today we're going to be talking about sort of a new paradigm for thinking about structured prediction, where our notion of decomposition gets away from the search-based setting where we kind of required some ordering on a sequence of decisions to a new setting where we think about dependencies between different components of whatever it is we're trying to build up. Okay, so finally the release deadline for homework 1 is set because it's passed, and the deadline is 2 weeks later on Thursday, September 26th. And so before we jump into basenets, I wanted to wrap up just with a brief discussion of applications of seek-to-seek models, because it's useful to kind of see how these are appearing in state-of-the-art applications. So the first of these is machine translation. And machine translation has now for a good number of years seen a lot of different people trying to apply models that were neural to the problem of machine translation. So some of the early ones were happening in 2013, and in 2014 that was a really well-received paper, Subscriber et al. 2014 at a conference now called Runtimes, and the basic model that they looked at was not too different from the same flavor of seek-to-seek model that we've been talking about in class. The two exceptions to sort of what we've seen in terms of sort of basic LSTMs is that they were, as their encoder, they were using sort of a stacked LSTM. So it was reading in with sort of 4 LSTMs at a time going left to right. And then their, maybe it was 4 or 8. And then their decoder did something funny, which was that it translated the sentence in reverse order. So it actually, here there's this sort of cartoonish picture of sort of a basic neural machine translation architecture, right? Where you could imagine we're translating some source sequence like ABCD into a target sequence XYZ. And what they did was instead to translate to something that was ZYX, where the reason for this, and then I guess a begin of sentence rather than an end of sentence. And the reason for this was that those LSTM cells were ostensibly supposed to be good at capturing long-term interactions, but in practice what they found was, well, when you feed the source sentence in, say the English sentence, it remembers a whole lot about the end of the sentence. And so if you just immediately then start translating to the end of the sentence backwards, it tends to do well. So here, oops. So these results, I can't zoom in on, are sort of representative of how we were doing in 2014. And so you can actually see that they kind of explored a bunch of different architectures for this task. And the actual data set that they were working with was sort of a standard WMT 14 English to French data set. And they were comparing with some prior work. And though in this particular case, the sort of state-of-the-art machine translation systems were this was still not it. And there were still other systems on other maybe broader collections of languages that were able to do better. But this was able to capture this clear improvement over some really strong baselines. And so here, what we're looking at are BLEU scores. BLEU scores are essentially this metric commonly used in machine translation because in machine translation we have this really tricky problem, which is you have this reference translation. Ostensibly, that's what you should be translating to. But who's to say that a similar translation that doesn't exactly match the reference isn't also a good translation? Okay, so the idea of BLEU score is that, well, at least in n-gram space, like in n-gram overlap, there should be a lot of overlap between whatever the output of your machine translation system is and whatever the reference in the actual test data set is. Okay? So this is sort of known to be a big problem with machine translation in general, is that automatic evaluation of these systems is really difficult. But in this case, so more overlap is better, and so higher BLEU scores are better. And here what we're seeing then are that there's sort of these different settings that they actually looked at for their own model, this bottom section of this table. And what they also did was they took an ensemble of collection of their trained models, where each of their own models was trained with a different random seed. And so when you took each of those individual models, they might actually make slightly different predictions. And so by ensembling them together, they were able to get something better than the individual STMs. So another point to note here is that we've been talking about inducing a greedy policy from a scoring function. That's not actually what they did here. They induced what's called a beam search policy from their scoring function. And beam search is something that we'll probably talk about later in the course, but essentially it's just this notion that you're doing sort of multiple greedy searches in parallel. And so the beam size is sort of how many different hypotheses you're entertaining at any given moment. Or however, how many different candidate sequences you're entertaining. So the last thing to note here is that they did some interesting visualization, and they essentially took these hidden state representations of sentences and then just used PCA to project them down to 2 dimensions. And so, so here we can look at some of the inputted sentences in their example. And so you can see they kind of took some toy sentences and fed it into their system and then wanted to see how do they actually relate to each other in this really low dimensional space. So what we find is that sentences like Mary admires John and Mary is in love with John, Mary respects John, all kind of cluster together in one corner, whereas the inverse of those, John admires Mary, John is in love with Mary, John respects Mary, are kind of in another corner. Okay? So syntactically, these look very different, but semantically, they share a lot in common.
How did you produce the embedding for the sentence?
Oh, sorry. So the embedding for the sentence, or the vector representation of the sentence, was just the output of their encoder. So what they did here was, so let's look at this little picture again. So they fed John admires Mary in as the source sentence, and then they took. So I guess that would have been, John admires Mary, and then the D here would have been end of sentence, and so they would have taken these 2 vectors as the representation of John admires Mary. Yeah. So that last hidden state was all that was handed off to the decoder, and so the whole model was training such that those little vectors there were working, or well, all of the parameters of the model were working really hard to encode this entire sentence in those short vectors. And so their theory was, well, if we just project them down to 2-dimensional space and then sort of visually look at how they cluster, we might find some interesting patterns, and that's what they found. Okay. So to anybody who's studied language, in some sense, this isn't surprising at all. That that the model would need to make sentences that carry similar semantics appear in similar parts of this high-dimensional vector space is sort of not surprising. But the fact that it actually worked maybe was what was surprising about this. Okay, so for acoustic speech recognition at the moment, there's a lot of different architectures that have been used in acoustic speech recognition. And the one that I want to kind of mention here is one that's a little bit different than the seek-to-seek models that we've talked about till this point. And that's because just like what we've talked about, it has an encoder and a decoder, but it also has this extra module called attention. And attention, it's not something that I want to talk about today, except that I'll maybe give the 30-second version of it, which is that you could think of attention as an extra module in your computation graph that allows the decoder to look back at the entirety of all the vectors that came out of the encoder, not just those last two. And the actual mechanics for how that works, there's lots of different ways that we can pull this off, but all of those mechanics kind of fall under this umbrella of attention, under this notion that you probably don't want to attend back to all of those vectors at once. You want to kind of allow the model to focus in on some specific ones. Okay, so then the key idea here is that we're building up, based on our input x, some hidden state representation h. And then we're gradually decoding one token at a time. And at every time step, we're now looking at that entire hidden state and attending to different parts of it as we spell out a transcription of the actual speech signal. Yeah.
So would you use attention with like an RNN or an LSTM, or would like an RNN with attention give you the same performance or better performance than an LSTM?
So you could use it on sort of whatever your encoder is. So we'll talk about CNNs at some point when we are sort of using vision as applications. So you could use an LSTM, you could use a CNN, you could use just sort of a basic Elman network. The point of attention is just that let's actually just jump back to this picture. Rather than saying there's only these two final vectors that feed into the decoder is now allowed to look at any of these arbitrarily many input or hidden state vectors representing the input. And the attention mechanism is going to focus in on some specific subset of them. And typically that happens by taking a weight. The simplest possible way to think about this is you could imagine taking a weighted average of all of those vectors that, because we have many time steps of vectors, the length of the input, and we're going to take a weighted average of those. And the question then just becomes, how do you actually come up with the weights for that average? So that's what's being done here. And we could spend an entire lecture just sort of talking about the different ways that you could do attention. But the basics of it are essentially fundamentally the same as all of the encoder-decoder models that we've talked about up until this point. Okay, so this is just sort of the more nuanced picture, which is that, okay, well, even their encoder is actually sort of slightly more interesting than I let on. So here we can actually see that they actually have this pyramidal bidirectional LSTM. So they're taking in something like a spectrogram representation of the actual audio. So you can think of this as taking the audio signal and representing it as an image. And then they're kind of taking individual columns of that spectrogram and feeding it in back and forth and gradually kind of condensing down the audio to fewer and fewer time steps of representation. And then once they've sort of coarsened it down from capital T time steps, oops, I guess we need to zoom out, from capital T time steps to
V time steps, then they have that actual attention and decoding. Okay, so so here are some results from Park et al. 2019, which used this listen, attend, and spell model. And so this is on LibreSpeech. It's 960 hours, and so at the top you can actually see some sort of classic machine learning approaches that are actually relying on hidden Markov models. And these are extremely strong baselines. And so these speech recognition systems are all, we're going to just focus on the side with LM, which is the setting where they were using a language model. And in that setting, you can see that, again, and let's focus in here just on the setting where the speech was clean. Okay, so they were kind of distinguishing clean speech from not so clean speech, okay? Meaning, maybe lots of background noise. And so in the clean speech setting, right, the lowest word error rate that anybody gets is here 2.97. Oh, actually, I guess there's actually a 2.95 here. So maybe let's, just for the sake of example, let's focus on the noisy speech. So I think this is going to be the winner. Is that true? On the second column, 750 here. Yeah. So here, that 7.50 is the best in this column. Okay. So this is sort of the classic system is actually beating all of the other ones in this noisy speech setting. Okay. And so this had been the case for quite some time, and all these people had been trying these sort of fancy end-to-end speech recognition systems that trained, connections, temporal classification models, and listen, attend, and spell models, and nobody could beat the classical system until this paper came along and figured out how to do it. And not only that, they blew everyone else out of the water. So it dropped from the state of the art being 7.5 to the following morning being 5.8. And so the way that they actually pulled this off was not to actually improve the model. It was the same listen, attend, and spell model, but they figured out how to actually augment the data set synthetically by generating a bunch of new fake training examples from the existing training examples, such that they were able to do a much better job of actually training this model and subsequently kind of change the state of the art. Okay, so maybe a point to make here is that all of these researchers had spent all of this time trying to get the model to just find the right way of connecting up the little pieces of the model. And it was really kind of someone who stepped back and took a totally different look at the problem and said, well, maybe we should be worrying about our data. That was what allowed sort of this great step forward from where things were. Okay, so then this last one is a little bit this is a little bit of a premature example application because the input here is not actually a sequence. But when we think about translation as sort of a model that gives the probability of an English sentence given a French one, we could say, well, by analogy, we could also think of getting the probability of an English sentence given an image. And so image captioning is sort of exactly that task where essentially the encoder looks a lot different. Okay, so now the actual input is this rectangle of pixels. And so the actual neural architecture that gives rise to this encoder vector, or the output of the encoder, is going to be a little bit different than sort of the LSTMs that we've seen so far. But then the actual decoding process is exactly the same. It's just another RNN language model. So this decoder is exactly what we're already familiar with here. Okay, and so here are some actual examples. Up at the top is the human's caption of this picture. So a close-up of two bananas with bottles in the background. And the best model was, a bunch of bananas and a bottle of wine, which, is not too far off. And then I don't know why the bananas are making such a strong feature in these examples, but so this was another one where the model seemed to do better. And then here, a man outside cooking with a sub in his hand is the actual human transcription, and then a man is holding a sandwich in his hand is the best model transcription. And so here, I mean, there is this little bit of a nuance that the human captured that the model didn't, right? This difference of, calling this a sub because the bread appears to be sort of like long, whereas the model just called it a sandwich. At the bottom is sort of a different model that was not doing so well. A man cutting a cake with a knife. Okay. So there's a bunch of examples in there. Okay, so we're walking away from seek-to-seek models armed with an incredibly powerful tool that can address a lot of different problems. So the actual sort of learning objectives for this course, I think, are pretty clear from what we've seen so far. Okay. So at this moment, you should have been expecting Bayesian networks to show up on the next slide. But I want to make a little bit of a diversion here to talk about computational complexity. How many of you have studied computational complexity? And if I asked you to prove that big O of 2 to the n is greater than big O of log n, you could write up a little proof of that. Okay, maybe half of you. Okay, so I just want to kind of brush up on some terminology here. So when we talk about analysis of algorithms, given a single algorithm, we might want to ask, will it complete in a given on a given input in a reasonable amount of time and space? And then another question we might want to ask is, given two algorithms, which one is better? So here, what I want to do is just sort of plot some curves that you should have in mind for basically sort of every aspect of this course going forward. And so what we're looking at is sort of a big O of 1 curve, where on the x-axis we're showing n, and then on the y-axis we're looking at sort of an example of a curve in the set, say, big O of 1 and big O of log n. So, okay. So here we're now looking at two curves. One of them is in big O of log n, and one of them is in big O of n. And so this big O notation is used to refer to a set of functions. And for that set of functions, we have the property that if you took a particular value of n, call it n0, and a particular constant c, then you could ensure that there exists some n0 and some constant c, such that whatever we're taking the big O of would dominate or be larger than that c times that function for values of n greater than n0. So these functions that we're looking at are sort of representative of these cases. Okay, so big O of n is sort of the kind of algorithm that we're sort of most familiar with. This is algorithms that have to look at every bit of the input to give us any sort of answer. Big O of log n are algorithms that we really like because they're sublinear, meaning that we can actually get away without even looking at all of the input to get an answer. Okay. So n log n is just going to be larger than linear, n squared is going to be larger than that, n cubed larger than that. And then we have one of our favorites, which is order 2 to the n. Is that a mistake on our plot here? something look wrong?
Over a larger period of time, eventually it will.
Yeah, so we didn't zoom out enough here. So functions that are in order 2 to the n are going to dominate functions in order n cubed, but you need to zoom out sufficiently far to make sure that they cross paths. Okay, so if you zoom out far enough, functions in order 2 to the n make everything else look as though it's basically order 1, right? Okay, so we are going in this class to be working, oh, do I have more? No, yeah. We're going to be working a lot with cases where the computation that we want to do is exponential in the size of the input. Okay, and so if it is the case that the problem, that solving the problem takes time exponential in the size of the input, well then that's fine if the input is really small. But if the input is not small, then the computation time is going to be so completely high that we just never would be able to complete it in our lifetime. Okay, and so what we're typically going to be concerned with is sort of bifurcation of these different names for computational complexities into 2 categories. One is things that are polynomial time, and then everything else. Okay. And things that are polynomial time tend to finish reasonably fast for our purposes. Okay, so in terms of complexity classes, it's useful to know of a few. So an algorithm runs in polynomial time if its runtime is a polynomial function of the input size for some fixed constant k. That would be something like order n to the k. And so we say, the class P consists of all problems that can be solved in polynomial time. Right? So in this picture here, we have some set P of polynomial time problems. Okay. So a problem for which the answer is binary, like a yes or no problem, is called a decision problem. And the class NP contains all decision problems where yes answers can be verified or proved in polynomial time. Okay. So what this means is just that you don't necessarily need to answer. So what we're not saying is that you can find out whether or not is a yes or no answer in polynomial time. Just that if someone gave you a proof of the answer, then you could verify it as correct or incorrect. So we say that a problem is, so this is that slightly larger circle here. So a problem is NP hard if you were given this sort of magic box that could solve it in order 1 time. If that would mean that every other problem in NP can also be solved in polynomial time by reducing it to something that could be solved by that little black box. Okay, and then lastly, NP complete is if it belongs to both classes NP and NP hard. Okay, so it's going to tend to be the case that we're concerned with mostly problems that are things that are NP hard, and then we'll think about how could we come up with approximations that are in the class P. Now, I didn't even bother looking at this picture, maybe because I have this bias that I tend to think that P is not equal to NP, that these are 2 totally separate classes, though nobody's ever actually been able to prove this, so we're still not sure. And so if we draw a Venn diagram like this, we actually also have to draw this Venn diagram, which is sort of in the hypothetical world where someone eventually proves that they're equal. Okay, so why do we start here? Well, what I want to talk about first is not so much Bayes-nets themselves, but thinking about how this search as structured prediction gives us insight into the computational complexity of some hard inference problems. So to do that, let's think about our running example, which was this part of speech tagging case, where this time I want to consider that we have a sentence like here. Find preferred tags. And here, in this sentence, find preferred tags, we could say that each of the words in it are actually, could either be a noun or a verb. And so the search space that we're going to work with is going to, as usual, have some start symbol, and then for find, it could either be a noun or a verb, and then for preferred, this could either be a noun or a verb, so that would be noun followed by noun, or noun followed by verb, or verb followed by noun, or verb followed by verb. Okay. And then likewise, tags could also be a noun or a verb, so that would give us noun, 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 or noun, noun, verb. Here, noun, verb, noun, noun, verb, verb. Okay. And this would just kind of continue along the way until we got the 8 possible taggings of this sentence. Okay. So, so where the last one is verb, verb. So what I want to think about is, suppose what we said was that to get a probability distribution over these possible tag sequences, we used the scores on the edges. Okay, so this should feel familiar. So what we're going to do, though, is we're going to say that all the scores on the edges are just some non-negative real numbers. And so, this might be 7, and 6, and 3, and 1, and 2. And so if we want to get, say, the score of a path, then we're going to multiply together all of these numbers on the edges. Okay. So 7 times 3 times 1 is 21. So we would say that the score of that first path leading to NNN is 21. Okay. Whereas the scores of the paths to noun verb are going to give us a score of 42, and so on down the line. Maybe down here we have 6 times 2 times 3, right? And so the score of this thing is 36. Okay, but then if we want a probability distribution, we're going to say, assume that the probability of a sequence y, given our sentence x, is proportional to the score. Okay. So then what we're saying is essentially this is the score of that sequence y, and the probability distribution, or the probability of that sequence y, is going to be based on these scores. So if it's proportional to the score, how do we actually compute, say, the probability for that first path? Yeah, normalize it by all the scores. So down here we could say we're just going to add up all of these scores, and whatever that is, we'll call it z. Okay? So the probability now is going to be 21 over z, and then 42 over z, all the way down to 36 over z. Okay. Great, so now we have probabilities for each of these different paths. And so at this point, we could start asking some questions. Like, one question that we might want to ask is, what is the what is the actual value of z? Okay, so if we want to compute z, how could we go about that?
Sum of multiple with a thing.
Right. Could we do any better? What if we just thought we had some trick where we could maybe just leave one out? And maybe, we'd just leave out one of those scores, but we would get pretty close, right? I mean, then we wouldn't have to compute them all, at least. Okay, so how bad of a problem could leaving one out be? Is it going to be a good approximation?
Would it depend on the size of the score?
Yeah, it totally depends on the one that we left out. So suppose we left out something like this VVM, okay? And maybe, over here, the score on this particular edge was something like 1,000. Okay, well now, all of a sudden, this thing is 12,000. And so if we had left it out, our approximation to z would have been terrible. Okay. All right, so question one, it seems that in order to compute that, we're going to have to do something that looks at every single leaf. Okay. How many leaves are there as a function of the size of our input? Yeah, 2 to the n if we have this setting where everything can be noun or verb. Okay, so that's not good, because that means that this is going to be exponential time. Okay, so, question 2. Let's see if we can do something that's a little easier. What if instead we wanted to compute some marginal probability, say the probability of some y2 given x? So now we don't want to compute all of the probabilities. We just want to compute this marginal probability, which is going to sum over possible values of y1 and possible values of y3 for the sequence, p of y1, y2, and y3 given x. Okay. Well, it would be nice if we could somehow compute this more efficiently, because think about it, we probably don't even need to look, say we made it even a little more specialized, where we just wanted to compute it for a specific case, like the probability of y2 equaling n given x. Okay. Summing over all path prefixes and path suffixes. Okay, so how many this was ordered 2 to the n. How many paths would we need to look at in terms of the length of our input n? If we wanted to compute, say, or let's call the length of the input t rather than n. So this is order 2 to the t. So if our input has length t and we want to compute a marginal probability, and let's generalize this a little bit to say, not necessarily 2, you might want to compute, the probability of y sub little t equaling now. Then how many paths do we actually need to look at to compute that?
To the power t minus 1.
Yeah, that doesn't sound good either. So it's still exponential time. It's just that all we did was we said, well, now we're only going to look at paths that have y2 equal to n. Okay. So we only need to consider paths that pass through those 2 yellow cases. But that's still going to be order 2 to the t minus 1. So still exponential time. Okay, well that's not good. All right, well, What about question 3 here, which would just be, is the highest scoring path? Okay, well maybe here we could use something like greedy search to find the highest scoring path, right? Then that would just be linear time. Does that sound like a good plan? Should we do greedy search to find the highest scoring path here? What would greedy search give us back? Let's fill in the rest of these numbers. Just for convenience, I'll make these all ones. So, what is the highest scoring path according to greedy search? Let's remember how greedy search works. It starts off at the beginning and it says, which of my neighbors has the highest score? Oh, 7 or 6? Well, 7 obviously. So let's go this way. And then it says, which of my neighbors has the highest score? Oh, 3 or 1? Well, naturally, let's go this way. 3. Which of my neighbors has the highest score? 2 or 1? 2. And so the final thing that it comes up with is NNV. What's the actual highest scoring path? Well, obviously this one, with the 1,000 at the end. Okay. So the only way that we could know that that is the highest scoring path is, again, if we actually look at the scores of all the leaves. So here again, solving this problem is going to require exponential time. Okay. So there's a sense in which everything that we're about to do with graphical models is going to come from the perspective that we want to be able to solve these problems and a couple more in polynomial time. And the way that we're going to go about it is by assuming that some of the scores up there are repeated. And by doing so, we're going to essentially be able to view this exponentially large search space in a polynomial size representation. And so once we can sort of collapse this exponentially large search space in on itself into something polynomial size, then we can come up with algorithms that capitalize on that polynomial size representation to solve these exact problems in polynomial time. So while the seek-to-seek framework and the learning to search space is sort of an incredibly powerful tool in our toolbox, it doesn't actually allow us to sort of solve many of the problems that we would want to if we want to work probabilistically with our models. Okay, and so if we want to reason about aspects of the model that are probabilistic. Okay. So, great. So there's sort of one sort of note in here about computing the total probability. Problematic. There's one. So problem 1 that's listed there. I didn't really set things up properly to talk about it because we were talking about a conditional distribution, P of y given x, whereas we would need to be talking about a generative distribution over both x and y in order to see the evaluation problem. So we're not going to be talking about that one just yet. In general, when we're talking about exact inference for graphical models, we'll often be sort of decomposing into the 3 problems that we just looked at, which are computing marginal probabilities, computing the partition function, which is the sum of all those scores, and computing the most probable assignment, which is the problem of map inference. And so we put a statement that was sort of loose on those. We said, okay, in this learning to search setting where the scores can be whatever they want in that search space, because our scoring function can look at arbitrarily large left context, then we're going to have these, the solutions to these problems are probably going to be exponential time. And in fact, we can make that a little more formal, and we can say that, so finding that most probable assignment is really an NP hard problem. Okay. Now, solving the other two problems of marginal inference and computing the partition function, we can't say that they're NP hard, because that would mean that they are decision functions, right? They're decision problems, rather, that they have a yes or no answer, or can be cast as that way. Sharp P hard is sort of the equivalent class of, it's the equivalent class that corresponds to problems where the output is some real valued function or some real valued number that we care about. So at the moment, I'm sort of purposefully eliding all of the notation on this slide. This is something that we'll return to once we've made sort of what this notation is referring to more crisp in our discussion of conditional and Markov random fields. Okay, so now let's talk about Bayesian networks. Okay, so if you took 601 with me, this is like one of my favorite examples. I'm going to actually force you to go through it again, and you can, or maybe you'll fall asleep. I don't know. I think most of you actually haven't seen this example, so we're going to jump in with it. So so imagine that you work at a 911 call center in Dallas, Texas. Okay, and so you receive 6 phone calls telling you that the emergency weather sirens are going off. Okay, so what do you conclude from this?
There's an emergency.
Yeah, what kind? Because you're in Dallas, so put some context on it. Yeah, tornado, right? That's what's in the slide title. You probably didn't guess. See, this is the problem with I don't have presenter view. I still haven't actually figured out. Oh, there we go. Okay, I can very slowly click. You probably didn't guess that hackers had come along and broken into the Dallas emergency weather system and set off the alarms, waking up tons of people at 11:40 p.m. on a Friday and all the way through 1:20 a.m. when they were finally shut off. Okay, so what went wrong here? Well, you guys just lacked, a proper Bayesian network to draw the right inference. Okay, so let's remedy that, and to do so, what I want to start with is a description of some variables. And the actual variables are going to line up with this problem, so we're going to think about these tornado alarms. And specifically, we're going to have binary random variables that represent the occurrence of some event. And so we'll have 5 of them. We'll say that one of them is t, and when t is equal to 1, that implies that a tornado occurs. So we're going to have another variable h, where we'll say if it has value 1, then those hackers successfully compromised the alarm system. The Dallas alarm system. Okay, if the random variable a is equal to 1, then we're going to say that 150 or more tornado alarms just went off in Dallas. And if c is equal to 1, then that's going to be a variable that's indicating some threshold like 100 plus 911 phone calls were just made. Okay. Now, there are other plausible explanations for why 100 plus 911 phone calls would be made. One of them might be, you know, there's a major fire in Dallas. Okay. So the key question here is how do we actually represent this joint distribution over these random variables? Namely, we have, you know, T, H, A, C, and F. And the question is, you know, how do we actually represent that joint distribution? Any thoughts? What if you were to use sort of the learning to search paradigm that we had just come up with? How could you decompose that joint distribution? Any thoughts?
Consider all of them to be independent.
Okay, so we could consider all of them to be independent, right? So that's definitely one possibility here. So here we could say this idea of independence, we could actually sort of write it out as, you know, the probability of this joint distribution, T, H, A, C, F, is equal to the probability of T times the probability of H times the probability of A times the probability of C times the probability of F. Okay. So I want to tie this back to our search space paradigm, because we could now say that for every random variable, T, H, A, C, and F, right, we could now have the two possibilities, right? So we can have our start state here, so that's our start state, and then T could either have value 0 or 1, right? And then for each of those values, H could have value 0 or 1. Same thing with A. This could be 0 or 1, 0 or 1, 0 or 1, 0 or 1. And suppose I told you that the scores on these edges were, say, 0.5, 0.5, and then here the scores were 0.7, 0.3, and then here the scores were 0.1, 0.9. Okay, and so if you want the, we'll just think for a second. I don't really want to keep drawing the search space out for C and F here. So let's just think of the joint probability of the first three, T, H, and A. So if you want the joint probability of T, H, and A being 0, 0, 0, you would just multiply together 0.5, 0.7, 0.1, right? And that would give you the joint probability. Okay, what are the scores on the other edges that I haven't drawn in?
They'd be the same because they're independent.
Yeah, because we just made this independence assumption, we actually know now that this is also 0.1 and this is 0.9. And this is 0.1, 0.9, 0.1, 0.9. Because they don't actually look at the left context here, right? They can't. The probability of A is just a function of A. It's not a function of what came before it. Same thing for the probability of H. These have to be 0.7 and 0.3. Or here, 0.1, 0.9, 0.1, 0.9. So you can see already that just by making this independence assumption, we now have a polynomial size representation of our exponentially large search space, because all we need are the red numbers. We don't actually need all of these blue numbers. Okay, so that's a good possible solution here. Does anyone want to give another possible solution?
Group a few events together and treat them as related, but in general separate into clusters.
Okay, so let's see, group them together into related but sort of separated by sort of clusters. So let me actually maybe draw a picture of that. Something we could say would be like, the event of a tornado occurring and, oops, gotta scroll down. So the event of a tornado occurring and the alarms going off, and then there being 911 calls, those should probably all be in a group. So let's actually connect those up with edges like this. So they're all connected to each other now. Okay, and then let's say as well, we want a group around, let's see, what are our other ones? Fire and which one am I missing? Hackers. Okay. Well, hackers definitely affects whether or not the alarms go off. So we should probably connect those two. Call them in a group. And whether or not there's a fire, that probably affects whether or not those phone calls are made. So we should probably connect those up. So we could say that the notion of group here is given by fully connected components, which in this case, there's actually one connected component here, one connected component there, and then the third connected component is these three. And if we were to take this idea to sort of its natural conclusion, we would get to Markov random field, but we're not going to get there yet today. Okay, so let's see. Idea 3. What do you have for me?
Instead of considering them independent, we can consider those probabilities to be conditional probabilities. That given t has happened, what is the probability of h being 0 and 1?
Yeah, so we could do something like, say, the joint probability T, H, A, C, and F here is going to decompose by the chain rule, right? We could say something like maybe the probability of C given F, A, T, and H, and then times the probability of F given A, T, and H, times the probability of, say, A given T and H. Oops, sorry, I have all these equal signs. Oops, you guys can yell at me when I am doing things off the page. Times the probability of T given H, times the probability of H. Okay. So now we could actually kind of conceptualize this in that same search space notion, right? Because now this is kind of like a RNN language model kind of thing, right? Everything is conditioning on everything that came before it. So the order is imposed by the order in which we did the application of the probability chain rule, right? So our search space must put H at the beginning, then T, then A, then F, then C. And it's going to fan out in that way. All right, now, in this case, when we have a score, this is our start node, out on an edge way at the end here, like the edge on this particular, whatever score we have on that particular edge, it could actually depend on the entire path leading up to that point. And so now we're actually back in a situation where all of those computations that we want to do are going to be exponential time. Okay. So apply the chain rule, sort of what this idea is. And this is really no different than having a giant table with a different score for each possible leaf node in this search space. Because in order to really represent this full distribution, we're going to have to spell out every single node in this enormous search space. Okay, so feels like we need one more idea here. And that idea, we'll say idea number 4, is that we're going to base it sort of on the causal notion of how these different events are related. Okay, so we're going to take this chain rule that we just wrote down, and we're going to reuse it by leaving some of the terms out. Okay. So what I mean by that is that, so we're going to say, well, here, where this event of whether or not those 911 phone calls was made, the probability of that certainly depends on whether or not there was a fire. Okay. But it doesn't really depend on whether or not the hackers compromised the alarm system. So why would I say that? Well, what I mean here is that if the hackers compromised the alarm system, they're not going to actually sort of have any effect until they actually turn on the alarms. But we already have a separate random variable for that, A. So we don't need both of them, right? The real causal reaction is the alarms go off, people hear them, and then they make the phone calls. Okay, so same thing we could say with a tornado, is usually like tornadoes are way far out of the city, okay? And then, you know, some weather guy notices the tornado is on its way and he sets off the alarm, and then people get nervous and they start making phone calls. Okay. So we could actually drop both of those from this right-hand side. And we could do that for a couple other ones. The fire probably doesn't depend on whether or not alarms are going off, or whether or not tornadoes are occurring, or whether or not hackers accomplished anything. And likewise, whether or not there's a tornado happening does not really depend on whether or not hackers compromise an alarm system. Okay. So now that we've done this, we've just sort of relaxed some of the dependencies that were in that original decomposition from the chain rule. But note that crucially, we had to pick an order for idea number 3. And I actually borrowed that same order down here. Okay? And what it gives rise to is our first example of a Bayesnet, or a Bayesian network. And specifically what we see is that we can draw a picture where we say, well, H doesn't depend on anything and T doesn't depend on anything. But the alarms going off depends on both H and T. And so we'll say that it's causally related to them, where the arrow is indicating the direction of causality. And then we could say further that the calls depends on whether or not the alarms are going off, but it also depends on whether or not the fire is occurring. Okay. Okay. So what we'll see is that this collection of independence assumptions that we obtained by sort of crossing things out of the chain rule, we can represent as this graph. But we can also go the other way. If you have the graph, we could have written down how this joint probability distribution decomposed. So what we have then is that our actual definition here of a Bayesian network is just that a Bayesnet, or Bayesian network, consists of a directed acyclic graph, which we can call G, and conditional probabilities P over random variables that we could call, say, y1 up to yj, such that the following representation holds. Okay, we're going to say that the probability of y1 up to yj is going to decompose as a product from, say, I equals 1 up to capital J here, over all of those random variables, where for each one, it's going to be the probability of yi given all of the parents of yi in that graph G. So here, you can see that this is exactly the property that we have in the decomposition above, where the parents of A are T and H, and so one of the terms in our joint probability is the probability of A given its parents T and H, and that holds for all of the random variables in our graph. Okay. So a Bayesian network generally has this form where we can decompose some joint distribution over, say, 5 random variables based on the actual topology of the graph. So 5 has one parent, so there's a term for x5 that conditions on its one parent x3. Right? And x4 has 2 parents, and so there's a term that conditions on its 2 parents 2 and 3. And so you can see there's one term per random variable or node in this graph. Okay. Great, so here's our definition again. Okay, so the question is, we have these kind of 2 parts, a qualitative specification that captures these causal dependencies between parts, and then a quantitative specification. So where does the actual qualitative specification come from? Well, it could come from prior knowledge of something about those causal relationships. It could come from some prior knowledge of modular relationships. I think this notion of modular relationships is sort of what you were talking about with groups, where we'll actually sort of talk about that notion in more detail when we get to our discussion of undirected graphical models. These ones are directed because the arrows actually, because the edges actually have arrows. You might just get some assessment from experts, or you might get some information from data. Or maybe you just like a particular architecture like an HMM because everybody likes HMMs. Okay, that's not true. The reason people actually like HMMs is that they admit polynomial time inference. You can solve all those problems that we have just been talking about in polynomial time because the HMM admits a polynomial space representation of the exponentially large search space. Okay. So there's lots of different forms that a Bayesnet could actually take. So we could say if we have discrete random variables, then the quantitative part of the specification is going to be actual conditional probability tables, right? Where for the probability of A taking on value A0 versus A1, we actually have this little table that is P of A. And then here we have P of B. And then here we have the probability of C given A and B. And for each possible of the 4 assignments to A and B, or here they're binary, we have two numbers representing the distribution over the 2 possible values of C. So you can see that each of these little columns actually sums to 1 in this conditional probability table. Okay, and at the bottom we have P of D given C. Okay. And so the joint decomposes into the product of just different entries in these actual tables. But things get more interesting if, for example, we have continuous valued random variables. Because then we could say that the probability distribution over their values comes from some probability density function, like that of a Gaussian. So here the distribution function for A is given by a Gaussian with mean mu A and variance sigma A. And then here B comes from another Gaussian with different mean and variance. And then C, which is the interesting one, has mean that is the sum of the value of A plus the value of B, and then its covariance are some parameters. Okay? And then D actually has, both dependence on some parameter, mu D, and also the random variable C. Okay? But the decomposition that comes from the graph still looks the same of that joint distribution. And then we could also have sort of some interesting mixture of sort of a combination of discrete and continuous variables. Okay, so one more detail here is that in a graphical model, we shade nodes to indicate that they're observed, meaning that their values are actually given. So if you want to talk about the distribution of x2 and x5, given some particular values for x1, 3, and 4, you could draw a picture where x1, 3, and 4 are shaded in. Okay, and we'll do this pretty regularly. Okay, so the thing that I want to leave with today is not here. So suppose you were trying to build a model, and this particular model, you wanted to have solve some problem, let's say, is that of energy disaggregation. So this is a fun problem. What it is you assume that you have access, so your observations are so continuous values for whole house electrical. So imagine that you go down into your basement and the big wire that's bringing all of the electrical into your house, you connect some sensor up to it. And then you go out to each of your outlets, say corresponding roughly to an appliance in your house, like your refrigerator or your washer or your dryer. And what you want to do is actually get a sequence for each of them. So you'd have Y sub fridge, and that would be, this is continuous values for whole house electrical over time. Okay. So you could think of this as roughly something like, a plot or something like this that represents your whole house electrical. And maybe it's a little more complicated than this silly picture, but then you have a sequence of times when you think that your fridge is either on or off. Okay, so most of the time we hope this course, and we could say that this is going to be further subdivided into little intervals. Okay, just for simplicity. Okay, and so we're going to have for the fridge values of 1 or 0 as to whether or not it's on. Okay. So maybe it's just on always, except for that one moment where the power went out, and then it's just on again. But then you're going to have another sequence of signals for, say, your washer, and that's only on some of the time. Okay. And then same thing with your dryer, except that with your dryer, it's always on after your washer. Right? So if the washer was on, then the dryer comes on right after it. So you could imagine then what we have here is a collection of random variables that we're trying to infer. Okay? And there's actually going to be, some interactions between them, like the washer and dryer case. And let's say that, we have this for, maybe many different appliances, all the way to, your 10th appliance, appliance 10. Okay. So in this case, if you think about for any given moment in time, how many different possible assignments are there to all of the appliances? If we assume that here there's, say, 10 appliances. So how many different states are there? Yeah, 2 to the power 10, right? So 2 to the 10, which is like what, 1024 different states. So one way that we could actually represent this problem would be using search-based structured prediction, where we just say that at every step along the way, you need to predict all 10 of them at once. Well, that sounds kind of bad, because this is going to be an enormous search space, right? It's going to blow up really fast. It's going to have fan out of 1024 at every step. Okay, so that's just one possibility. So we could say so search-based structured prediction with 1024 fan out. Another thing that we could do is we could come up with some order. Oops, sorry. So these are different ideas we could use to solve this problem. We could come up with some specific ordering of these random variables. And we could first, say, predict the state of the fridge, then the washer, then the dryer, all the way down to appliance number 10. And then we could circle back up and do the next time step. Fridge, washer, dryer, appliance 10 at time step 2, and then at time step 3. Okay, but that means that each state, or each time step, would require 10 decisions, right? 1 for each appliance. So now your search space, the columns of your search space don't correspond to time anymore. You actually have to grow them out horizontally. Okay. So that's going to blow up the search space in sort of a different way. Okay. So the third possibility here is that we could actually say, well, what if we just thought about the actual sort of behavior of this data? Well, practically, what we have is something like we have some x at time 1, x at time 2, x at time 3. And we also have something like whether or not the fridge is on at time 1, time 2, and time 3. And so the actual electrical output is going to depend on the state of the fridge at the corresponding time step. But then we're also going to have the state of the, say, washer at time 1, washer at time 2, washer at time 3, and the dryer at time 1, the dryer at time 2, the dryer at time 3. And those are also going to influence causally the actual sort of current value of electricity. Okay, but just knowing what the actual state of these devices on isn't going to tell you much about what's coming next. So what we could also do is we could say, well, if you want to, sort of get a sense of what's going on, you should probably also, have some connections between these variables and some connections between these variables. Because now, what this allows us to say is that, the behavior of the whole electrical system is kind of related to what was going on in the past in the whole electrical system. But also within a little sequence here, the behavior of the dryer, whether or not it's on, depends on whether it was just on or not. And if you have some notion of a